Welcome to today's presentation, brought to you by Melanie Dickie, the ABMI and Biodiversity Pathways. Before we begin, I'd like to start with the land acknowledgement. The ABMI respectfully acknowledges that our work takes place on the territories of Treaties 6, 7, and 8, traditional and ancestral lands of First Nations and Métis people, whose histories, languages, and cultures are directly connected to the biodiversity that we monitor. We acknowledge the traditional teachings of the lands that we work on, and that reciprocal, meaningful, and respectful relationships with Indigenous peoples make our work possible. And now to introduce Melanie Dickie, our speaker for today. Melanie is a senior caribou ecologist in both the ABMI Science Center and the Wildlife Science Center of our national affiliate, Biodiversity Pathways. Melanie's work revolves around understanding how landscape change triggers ecological pathways that contribute to caribou declines, and testing management actions that can be used to address these pathways. So without further ado, I will pass things over to Mel.
Awesome. Thank you, Brett. Can you just confirm that you can hear me all right?
I can hear you.
Awesome. Okay, so thanks everyone for coming today. I want to talk about a paper that we had come out just a couple of weeks ago in Global Change Biology. I tried to make the webinar itself fairly short, so there's lots of time for questions and answers at the end, and I look forward to discussion. So I'll go ahead and jump right in. So the story that I'm going to be talking about today takes place in the boreal forest of Western Canada, particularly in Saskatchewan, Alberta, and a little bit of implications over into British Columbia. And the boreal forest occupies much of Canada. I've got it drawn here in green with paint, but it gives about the right distribution of the boreal forest. And the Western boreal forest is home to woodland caribou, moose, wolves, and bears. There are other critters on this landscape for sure, but these are the critters that I'm talking about mostly today that are implicated or impacted by a relatively new player to this system, white-tailed deer. So white-tailed deer have been moving northward as well as eastward from the United States up into Canada over time. A lot of that movement was driven by things like agricultural expansion, the management of predators historically, and more recently they're making their move into the boreal forests past these agricultural lands. And that's what we're talking about here when I mean the expansion into the boreal. So back in 2011, Dave Latham put out some research that showed that there was an increase in the abundance of white-tailed deer from the mid-90s to the mid-2000s. And at the same time period, there were relatively stable moose populations. So white-tailed deer are this relatively novel species to this part of the boreal forest. The study took place around Fort McMurray, whereas moose are kind of that native ungulate species. And at the same time, in the shift in the abundance of species, we also see a shift in the diet of the native predator species, wolves. So here we have the percent occurrence of each of the different prey species in the diet of wolves in these same two time periods, in dark black for the 90s and gray for the 2000s. And what we see is that when the abundance of white-tailed deer increased, that availability of this prey species increased, wolves shifted their diets, and there was a marked increase in the occurrence of white-tailed deer in the diet of wolves, and a decline in the occurrence of the native moose in the diet of wolves. There is also a bit of a signal on the right there that there was an increase in beaver in the diet of wolves, but that's a story for another day. But it is an interesting piece of this puzzle. And we know that white-tailed deer can act as ecosystem disruptors in many places, but what I'm talking about when I say an ecosystem disruptor in the boreal forest is that in places where we have a higher abundance of white-tailed deer, there can be higher populations supported of their predators, like wolves and black bears, which incidentally predate on caribou, a threatened species in the boreal of Canada, creating this apparent competition between whitetails and caribou that's mediated through this shared predator. Now, one of the reasons that we think white-tailed deer are expanding and increasing in abundance is because the conversion of mature forest to early cereal vegetation through human land use creates an abundance of forage and food subsidies for these white-tailed deer. But the degree in which that happens, particularly in the boreal forest, is unknown and is in question because the direct landscape impact of humans is less than 10% of the landscape. This is what human footprint looks like in the province of Alberta. And in the northern boreal, what we see is a lot of the disturbance looks a little bit like this. This is a seismic line where we cut down the mature forest and then a flush of early cereal vegetation comes back in its wake. Linear features or seismic lines are one of the predominant features on this landscape, but there are other disturbance features as well, such as well pads or cut blocks. But one of the things that we can see on this map is that as we move northward through the province of Alberta, we get a decline in the direct amount of human footprint on this landscape, where much of that boreal forest is in the 0 to 10% directly disturbed range. And concurrent with this gradient in habitat alteration going from north to south, we also have a gradient in climate going from south to north. Here I'm showing temperature as an indicator of climate, but a variety of climate variables look relatively the same. And the main story here is as we move north, there's a change in the climate. For example, winter severity gets more intense as we move north, and this is confounded with that south to north decrease in habitat alteration. And we know that climate can also play an important role in the distribution and abundance of white-tailed deer. So here I'm showing the probability of white-tailed deer presence at a particular site across Alberta, declining as winter severity increases. And that vertical red line on the left-hand panel is where we expect to have deer present at a particular site, and that's then mapped onto the province of Alberta on the right in the 60s. And what we see is that line of deer being more likely to be present at a site is moving northward over time. So now in the 90s, it's farther north. So we have this confound between climate and habitat alteration. And the objective of this particular study was to disentangle the effect of habitat alteration and climate on white-tailed deer densities, which of course has implications to how we manage deer themselves. And we also need to keep these implications in mind when we're managing caribou, which are, again, a threatened species in Canada. But this also generally just has implications for understanding abundance and distribution in quickly changing landscapes. And I say that because I want to point out that this problem is not unique. Often the impacts of human habitat alteration and climate are confounded in both space and time, and it can be very tricky to disentangle these two. We did it by leveraging the provincial boundary between Alberta and Saskatchewan. Now, obviously, critters don't care about provincial boundaries, but what it did is it provided this contrast in habitat alteration that was decoupled from that north to south gradient in climate. So as here in this map, the green is where habitat alteration is mapped, and this is mapped according to the caribou recovery strategy. And then in gray is disturbance overlaid on top of that mapping boundary. So anywhere we can see green peeking out, that's undisturbed, according to the federal recovery strategy, which essentially takes direct human habitat alteration and buffers it by 500 meters. And then where we see gray shading, it's disturbed. And it's pretty visibly obvious that disturbance decreases quite a bit as we move from Alberta over the border into Saskatchewan. And Alberta is actually 3.6 times more disturbed than neighboring Saskatchewan. So we use that contrast in low alteration to high alteration that you can see in this map to disentangle from that south to north gradient in, for example, winter severity or climate more generally. And we placed camera traps in each of these black rectangular areas to estimate the density of white-tailed deer in each of those camera clusters. So if we look at one of those camera clusters, it looks something like this, where they're about 12.5 kilometers long and 4 kilometers wide, and 25 cameras were randomly placed within that camera cluster area, and we used time in front of camera to estimate the density of deer for each year for each camera cluster. And we left these cameras out from 2017 through 2021. So there were 5 years of, 2022. So there were 5 years of data monitored. Then we took those deer densities and we modeled those as a function of human habitat alteration. So the total percent area altered by human land use using the ABMI's human footprint inventory and the analogous Saskatchewan inventory. We used a multifactorial analysis to create an indice of climate. So it's similar to a PCA, but it counted for repeated sampling across years. And we used a whole bunch of different climate metrics that have been previously linked to white-tailed deer survival and recruitment and collapsed those down into 1 or 2 dimensions. The first dimension, which explained the majority of the variation, can be essentially interpreted as a winter severity type index, where it measured the length of the winter, the cumulative snow depth, so how much snow there was, and the temperatures of the winter. We also know that habitat context matters for the abundance of white-tailed deer. So here I'm talking specifically about habitat productivity measured using delta EVI, or the change in the Enhanced Vegetation Index, which is essentially a measure of deciduousness. And I've got that mapped here as an example, and our study took place right about here. And we know that delta EVI predicts deer densities to some degree, and we wanted to account for this. So the model looked at habitat alteration, interacting with climate, as well as habitat context, or that habitat productivity. So I'll take you through the results. On the y-axis, we have the density, so the number of deer per kilometer squared. On the left-hand panel, we have that percent habitat alteration. On the right-hand panel, we have that winter severity dimension 1 from the MFA analysis, and it essentially corresponds to longer, snowier, colder winters. And importantly, I'll also have the raw data colored by delta EVI, or that habitat productivity, because we always need to keep in mind that baseline habitat productivity, where the brighter colors, the brighter greens and yellows, are more productive areas with higher delta EVI. And then I've just got the data parsed out by year for you to visualize. So the first thing to see here is that we see maybe a hint that deer density increases with increasing habitat alteration. So as we move from that kind of 0 to 5 range up to the 12 to 17-ish% disturbed, there does appear to be a bit of an increase in deer densities. One thing to keep in mind, though, is that the data parses out quite a bit visually from delta EBI. So when we account for that habitat productivity in the model, there is no significant effect of habitat alteration on deer densities, even though there is that tendency. On the other side, we do get a significant decrease in deer densities as winters become longer and snowier and colder, even when accounting for that delta EBI. Now there is, of course, this one outlier area where we have higher deer densities than expected based on the winter severity, and that was largely explained by high habitat productivity at that site. So here, the main take-home is that we have a tendency for higher habitat alteration to increase deer densities, but we have that significant effect of winter severity, decreasing deer densities. And when we look at the coefficients from the model, the effect of climate is twice that of either habitat productivity or climate on their own. So, what might this mean for caribou? This is, in essence, a deer paper. It's all about white-tailed deer, but the rationale behind the study is, of course, driven at least in part by how we manage caribou on this landscape. And there are multiple pathways in which human habitat alteration influences caribou. We have, again, that conversion of mature forest to young early xeroforest, which creates an abundance of species like deer. I didn't mention before moose, but in some systems we also have an increase in moose densities, which leads to more wolves and incidental predation on caribou. We also know that linear features, so things like seismic lines, roads, and pipelines, create movement corridors that predators, particularly wolves, travel faster and farther on, which is thought to increase their encounter rates and thus predation on caribou. But now we also have this third piece to keep in mind, and that is climate change that can not only affect the vegetation and the habitat itself, but it can also contribute to supporting the abundance of ungulates by reducing winter severity. And we need to be keeping this additional piece in mind when we're managing caribou. Because, say, in a place where climate change is supporting abundant white-tailed deer populations, if we were to remove these effects of habitat alteration, we still have this pathway that can be triggering changes that lead to increased predation on caribou. Now, that doesn't mean that we don't do restoration. It means that we think very carefully about it. So it does beg the question of, will habitat restoration support self-sustaining caribou on its own? And in some places, it very well could. And in some places where we have abundant white-tailed deer, even if we were to return that landscape disturbance, there might be this new player in the system that kind of makes it less effective. And we might need to consider additional management strategies to deal with those white-tailed deer at the same time. And my kind of push here is, well, let's find out. Let's stop wondering and let's test it at a large scale. So we should try to test habitat restoration, ideally in a place where there is, one, already a strong deer population there, and two, in a place where there just quite isn't a deer population yet, to test the difference between those two. Can habitat restoration address those ecological pathways and increase caribou populations? and what happens if there are deer or are not deer in that system. And the other thing that we could do is to understand whether or not habitat restoration in those places where deer have not yet established because winter severity is too tough, will that build ecosystem resiliency towards the further establishment of whitetails in that area? So yes, climate is one of the main drivers of white-tailed deer abundance, but there was that tendency for habitat alteration. So if we remove that tendency, do we kind of buy ourselves a little bit more resiliency in the landscape? And I just want to take this back to the idea that this is not a unique problem. We're now well within the United Nations decade on ecosystem restoration, and we know that in many places, both human habitat alteration and climate change are having influences on biodiversity loss and species declines. And we really do need to understand the relative effects of those two different stressors to be able to manage them effectively. And with that, I'll wrap it up. Thank you to all the funders, the Regional Industry Caribou Collaboration, NSERC, and MITAX, as well as all of my collaborators at the Wildlife Science Centre, UBC, ABMI, and University of Alberta, as well as the Government of Alberta. Thank you very much.